In this Navier-Stokes example solution, we're going to say we have a belt that's moving vertically, so just a planar belt looks something like this. And so that's the belt. And it's moving upwards vertically at a velocity capital U. And there's a liquid bath adjacent to the belt, so there's some liquid, there's the free surface. And oops, let's see if I can spell the word belt, liquid here, so liquid. And because the belt is moving upward, it's going to draw some of that liquid up with it. So we're going to say it's moving up along the surface of the belt. And the thickness of that film, we'll say, is H. So the liquid's moving upward with the belt. Gravity's acting downward. And we have atmosphere out here, just open to the air. So the belt is pulling the liquid upward through the action of the no-slip boundary condition. So what we want to do in this problem is determine the velocity profile in the liquid as it's moving up up with the belt. So I want to know what the velocity profile is there, and I also want to know the volumetric flow rate of the liquid as it's moving upward. So what's the rate at which volume is headed up that belt. So this will be a Navier-Stokes solution problem because we want to know the velocity profile. And to find that velocity profile, we need to solve the fundamental equations of fluid motion, which are the continuity equation and the Navier-Stokes equation. So in order to do that, we're going to take our standard Navier-Stokes solution approach. We're going to make a bunch of assumptions to simplify the problem, and then we'll solve the Navier-Stokes equations subject to those assumptions. So assumption number one is I'm going to say I'm dealing with a steady flow. We're not told about how this is varying with time or anything like that, so it's very reasonable to assume that we're dealing with a steady flow in this particular case. So nothing's changing with time. We'll also say that we're dealing with a planar flow, meaning that nothing is changing in and out of the page. Let me put a coordinate system on here so we can refer to which direction I'm talking about. So we'll say that upwards is the y direction and horizontally is the x direction. So when I say it's a planar flow, that means that there are no variations in the z direction. And really, and actually the z velocity in this case would be 0. There's no reason the flow would be going in or out of the page. Okay, so we have that. We'll also assume that we have fully developed flow in the y direction, which means that the velocity profiles aren't changing in the y direction. So that one's a little more of an assumption. So when I say it's fully developed in the y direction, it means that if I looked at the velocity profile here and the velocity profile here, they would look the same. It's not changing in the y direction. Now that's not a very good assumption near the interface here, right? Because in the interface, the thickness is changing, and it's going from basically a nominally stagnant fluid to a fluid that has some y velocity to it. So the fully developed assumption wouldn't be a good one in this kind of developing region here, but it might be a good one as you get far away from the surface there. So once we're up here, that fully developed assumption in the y direction is actually probably a good one. So you have to keep that in mind, what the limitations of your model are. And then number 4 is that gravity acts in the minus y direction. We can just see that from the picture. So g sub y is just minus g. We see that right over here. Okay. So those are the assumptions we'll make, and some other ones that I won't write down are that we'll deal with an incompressible liquid. The liquid being incompressible is a pretty good assumption. We'll assume that it's a constant dynamic viscosity as well, and that the fluid's Newtonian. So those are assumptions that I'm making implicitly here. So we'll go ahead and start with the continuity equation. This is just conservation of mass for a very small control volume. We're dealing with the Cartesian coordinate system here, so we can write this out without looking at a table. Of course, it's fine if you look look up the continuity equation in a table. It's no problem. I wouldn't expect you to memorize it. So we can simplify this from our assumptions. So first of all, this term here, the du z dz, is going to be 0 because of assumption number 2, that it's a planar flow. And then this du y dy is going to be 0 because of assumption number 3, that it's fully developed in the y direction. And as usual, if you've looked at any of the other Navier-Stokes example videos, this is the preferred approach that I hope you take when you solve these problems, is when you set things to 0, when you simplify them using your assumptions, just put a number to indicate why these terms are 0 or why they have the value they have. Just refer back to those assumptions. So you can see now that the x velocity doesn't vary with respect to x. Now in general, the x velocity could be a function of x, y, z, and t, right? Well, this equation, the continuity equation, says that dux does not vary with x, so that's gone. We know it doesn't vary with y because it's fully developed in the y direction. We know it doesn't vary with z because it's a planar flow, so that one goes away. And we know it doesn't vary with time because it's a steady flow. So it doesn't vary with anything, so at best, ux is going to be a constant. And in order to find out what that constant is, we can simply look at the boundary conditions. We can see right here along the belt, right here along the belt surface, where x is 0, there is no x component of the velocity. It can't go through the belt. So that x velocity, that constant would be 0, and the x velocity would be 0 everywhere. So no flow through the belt just means that ux is 0 everywhere. The constant is 0, so that means ux is 0 everywhere. And we'll call this condition number 5. Because it's not really, I didn't make an assumption for that here. I actually derived it. So that's not an assumption. I'm calling it condition number 5, just so I can refer back to it. It would be perfectly fine if one of your assumptions up here was that you were dealing with a laminar flow. So you could make assumption 5 here, laminar flow, ux is equal to 0, meaning that the flow is going in layers up the belt. And that would be fine. We just kind of derived it here. So we're only able to solve this problem if we can make these assumptions that it's steady and planar and fully developed. And that only holds true if you're dealing with laminar flows. If it was a turbulent flow, then we couldn't say it was steady. We couldn't necessarily say it was fully developed in the y direction. And we wouldn't be able to solve the problem by hand in that case. So we're really, this really just means that we're dealing with a laminar flow. Okay, so now the next thing we want to do is solve the Navier-Stokes equation. What we want to do is solve the Navier-Stokes equation in the y direction, because that's the velocity profile component that we care about. It's how the velocity is changing, or what the y velocity is, right? And we want to see how that varies with x. So we'll want to solve the Navier-Stokes equation in the y direction, because we want to get that u sub y velocity profile. So we can write that out. And again, you can refer to a table to get what this equation looks like. Or if you've done enough of these, you'll have it memorized. So it's just a lot to write out, so we'll just take a moment here while I get it all on the screen. Okay, so there's the Navier-Stokes equation in the y direction. All this equation is F equals ma. Here's our force terms: pressure force, viscous forces, body force, and this is our mass term times acceleration. I say mass, this is really a density, but it's mass per unit volume. Everything in here is, it's like force per unit volume is equal to mass times acceleration per unit volume. This term in parentheses here is your Lagrangian derivative of the y velocity component, so it's just the acceleration in the y direction. Okay, so there's our Navier-Stokes equation, and just like the continuity equation, we'll go ahead and simplify using our assumptions. So I'm going to shrink this down so I can see my assumptions a little more easily. So the first term is 0 because of assumption number 1, that it's steady. Second term is 0 because of condition number 5. We found that the ux velocity was 0 everywhere. The next one is going to be 0 because it's fully developed in the y direction. That's number 3. Next one is 0 because it is a planar flow, so that's number 2. I'm going to come back to this dp dy in just a moment, but for the time being, I'm going to just skip that. D squared uy dx squared, that one we can't say anything about. There's nothing in our assumptions or continuity equation that we can do for that one. So that one needs to stay as is. But the next one we can set to 0 because it's fully developed in the y direction. The next one is 0 because it's planar, so that's number 2, assumption number 2. And the g sub y is equal to minus g. That's from number 4. Okay. So we're doing pretty well so far. So let's go ahead and now let me talk a moment about dp dy here before we go any further. This is how the pressure in the flow varies with respect to the y direction. Okay, so it's how the pressure is varying in this direction. In order to discuss that, I'm going to go about this kind of the long way. Let me write down the Navier-Stokes equation in the x direction, so that all of this is kind of mathematically clear. So if I write the Navier-Stokes equation in the x direction, and unfortunately I just have to write the whole thing down, it just takes time. Almost there. Okay, so here's the Navier-Stokes equation in the x direction. First term is going to be 0 because it's steady. That's number 1. Actually, all of these, well, there are different reasons why they're 0. So it could be 0 because it's steady, but it could also be 0 because ux is 0 everywhere. So this next one is 0, number 5. Next one is 0 because of either number 3 or number 5. Next one is 0 because it's either because of number 2 because it's fully developed. I'm sorry, because it's planar, or because ux is 0. This is 0 because of number 5. This is 0 because it's fully developed, or because ux is 0. So that I'll just put number 3 for that. That one's 0 because it's planar, or because ux is 0. Gx is 0 because there's only gravity in the x direction, so that's number 4. So everything is 0 here except dp dx. So I've said everything. I've made an assumption about all of these, or we just know ux is 0. So in the end, what we'll get is dp dx is equal to 0. So there is no pressure gradient in the x direction. So this just means that there's pressure is constant in the x direction. Okay, and you could do the same thing in the z direction. You'd find that there is no pressure variation in the z direction. So let's go back up to the picture and see what that means. So that means as I move horizontally across here, the pressure remains constant in the fluid. So it's P atmosphere here. So it'll be P atmosphere at every point horizontally, correct? That makes sense because I just proved down here that there is no pressure variation in the x direction, so it has to be P atmosphere all the way across. It's P atmosphere at the surface here, and dp dx is 0. But that's also true down here as well, right? It's P atmosphere here, so that means it's going to be P atmosphere everywhere inside here also. So that means that it's going to be P atmosphere vertically as well, right? Because if it's P atmosphere across any horizontal line, that means there is no variation in pressure vertically either. So that then means that dp dy is going to have to be 0 because we said there's no pressure variation in the x direction or the z direction. And if that's the case, then there can't be any pressure variation in the y direction because it's P atmosphere all the way along the surface. So dp dy will be 0 for that reason. Okay, so hopefully that makes sense. That's the trickiest part of this whole problem, is recognizing that dp dy is 0. And it comes about because of this kind of argument that dp dx and dp dz are 0. And since it's atmospheric pressure everywhere on the boundary, it has to be atmospheric pressure everywhere in this whole flow. All right, so again, that's the trickiest part. What we can now do is take the y Navier-Stokes equation component. All we have left is that term, d squared dy dx squared, and that'll just be equal to 0. So let me jot that down all the way down here. Switch back to black ink. So we have d squared u y dx squared is equal to 0. And the y velocity in general could be a function of x, y, z, and t, but we know it's not a function of t because it's steady. We know it's not a function of z because it's planar. We know it's not a function of y because it's fully developed in the y direction. So at best, the y velocity is a function only of x. So what that means is that this partial derivative, which implies that it's a function of more than one variable, is really just an ordinary derivative because it's a function only of x. So we can solve that differential equation. It's pretty straightforward. Let me just integrate once. We'll get du dx is equal to a constant. And then we integrate a second time. Oh, actually, you know what? I made a mistake here. This is not 0. Sorry about that. I should have been more careful. When I went back up here, I missed the fact that we have the body force term, the rho minus g. So this equation, sorry about that, should be mu times d squared uy dx squared is equal to a rho g. That's what that should be. Sorry about that. So then this just looks like this when I divide through by the viscosity. And then when I integrate once, I'll get duy dx is equal to rho g over mu times x plus some constant. And then I'll integrate one more time. There we go. So that's our general velocity profile in the y direction. And you see that just generally speaking, it looks like a parabola, but we still need to find out what these constants are. So we'll go ahead and apply boundary conditions. Now, one of the boundary conditions is probably pretty obvious. We go back up to the picture. You see we have this belt surface here. So we know that's moving at velocity capital U. So from the no-slip boundary condition, the y velocity of the fluid at x equals 0 should be equal to capital U. So that's a no-slip boundary condition. So let's write that down. So no slip on belt. So what that means mathematically is uy when x is equal to 0 is equal to capital U. By the way, this is I like, when I solve these Navier-Stokes solution problems, I like doing it this way. I like saying what things are physically first, and then translating that into mathematics. I did the same thing up here with the assumptions. I put everything in words first, and then say what it means mathematically. I think it just helps communicate what it is you're doing, and it also helps cement the physics, that you better understand physically what's happening. Okay, so with that boundary condition in mind, we'll see that C2 is equal to, oops, it's not 0. That C2 will end up being equal to capital U. Okay, so we have that one. Now we need a second boundary condition, but that second boundary condition, it's not exactly clear what it is. Let me just show the picture again. Here's the belt moving upward at velocity capital U. Here's the liquid, there's the free surface. And let me just put the coordinate system back in here. Here's y, here's x. So we already made use of the no-slip boundary condition on that surface, but, oh, and by the way, this is width h. But we haven't, we need a second boundary condition, and it's not clear. This surface, it's not touching any, it's not touching a belt. Really what it's touching is just the atmosphere here. Actually, there is a no-slip boundary condition on this surface. What it says is that if the liquid velocity on this surface should be the velocity of the atmosphere on that surface as well. So the atmosphere is actually not stationary here. If the liquid is moving upward, let's say, on that surface, then the atmosphere has to move with it from the no-slip boundary condition. The no-slip boundary condition holds both at solid boundaries and fluid boundaries. So right at this free surface here, the liquid and atmosphere have the same velocity. Unfortunately, we don't know what that atmospheric velocity is there, so we can't really make use of it. Now, another boundary condition we can make use of is that the stresses are continuous across the interface. So not only are the fluid velocities continuous across the interface, but the stresses, so like the normal and tangential stresses, are continuous. So we're going to make use, for our second boundary condition, that the shear stress at that surface is continuous. So we'll say shear stress is continuous at the free surface. And I'll tell you in a moment why that's helpful for us. So that means that the tau stress, the shear stress there will be the shear stress on the x face in the y direction, evaluated when x is equal to h, right? Because that'll get us right on the free surface here. And that will equal, so this is for the, what do we call it? Is it water? It's a liquid, so we'll just call it liquid. That should be the same as the shear stress on that same face for the atmosphere or the air, right? Those should be the same. Okay, and let me just write that out for a second. The liquid net dynamic viscosity, we'll just call it mu sub L. And the shear stress there will be du y dx, evaluated at x equals h. And we'd have this kind of a similar thing over here for the air. Okay, so we're doing this for the air. All I'm saying is that right at that interface, right here, I'm saying that the shear stress is a constant. Now, let me look at this for a second. Now that I've written this out, we don't know what the velocity profile is for the air. We know what the velocity profile is for the liquid. We've got it up here. But we don't know what it is for the air. But it doesn't matter. And the reason I say it doesn't matter is because think about the difference in the dynamic viscosities between these two. Right? So typically, the dynamic viscosity for the liquid will be much, much larger than the dynamic viscosity for the air. Right? I don't have it with me offhand, but the dynamic viscosity for water is definitely much larger than the viscosity for air. So it's very reasonable to assume that this on the right-hand side is zero, that it's a negligible shear stress that the atmosphere is exerting on the liquid. Hopefully you understand that, but basically I'm saying that the atmosphere is not tugging on that liquid in any substantial way. Certainly the belt can exert a pretty large shear stress. That's what's carrying the liquid upwards. But the atmosphere, because the air has such a small dynamic viscosity, it can't exert much of a force on here at all. And we don't even know what the velocity profile is, but it's probably a relatively small gradient anyway. So this whole term on the right-hand side is pretty small. So what we're saying here, instead of saying that the shear stress is continuous at the free surface, we're kind of saying that the shear stress is about zero at the free surface. Okay? It's just that the atmosphere can't exert much of a shear stress on the liquid because it just has such a low viscosity. So the shear stress in the liquid is about equal to zero right at that free surface. So we can make use of that as our second boundary condition. So that's the hardest part of this whole problem is, well, I guess there are two hard parts. The first one was just recognize, that the pressure, fix that. First kind of hard part was figuring out the PDY was zero, but then the second part that I think is tricky is knowing that the shear stress at that free surface is about 0. And that's really our other boundary condition. So we can now find the velocity gradient in the fluid from up here. So let's do that. So we'll have mu L times rho G over mu L. That's the viscosity up here is just mu L, so I'll just write mu L down here, times X plus C1 is equal to 0, right? So all I've done is just taken the derivative here from this. And then we have to plug in an x equals h because we want it specifically at that free surface. So the x is equal to h there. In general, the viscosity of the liquid is not 0, so we can divide through by that. And what we'll be left with then is C1 is equal to minus rho G over mu L times h. So now we have everything we need to plug back in to our expression up here. We now know C2, we now know C1, we can plug it back in and rewrite the expression. So let's do that. So if we plug in and do some algebra to rearrange it, I'm going to just write it, I'll just save you all the algebra. This will be a rho G all over 2 mu times x squared minus G, a rho G H all over mu times x plus capital U. And that is our liquid velocity profile. And let me just double check that by plugging in my boundary conditions. So when x is 0, I should have it equal to capital U. So 0 there, I get my capital U. And if I take the derivative of that, dy dx, that'll be rho g over mu times x minus rho g h over mu. And then I plug in when x is equal to h, right at the free surface, that comes out to be 0. So the shear stress on that free surface is 0. So that's this boundary condition right here. So that works out as well. So that's our velocity profile, and it looks like a parabolic profile. We are now asked, so that's part A of this problem. Part B of the problem is to find the volumetric flow rate in the film per unit depth. So just to go back to the picture here, so here's our situation. Let me just kind of sketch in what the velocity profile might look like. So we're certainly moving upward. Let me put this in a different color, put it in red. So it's moving upward at a velocity u right at the surface, but it may actually move downward at the free surface. We don't really know exactly. So the velocity profile may look something like that, for example, where that's kind of a parabolic shape. It all depends on the relative magnitudes of these various quantities in the expression here. But what we want to know is, what is the volumetric flow rate headed upward here? So the way I'll find that is I'll just integrate that velocity profile over the area. So since the velocity profile varies across the distance x, I'm going to have to do this in little bits. So the velocity profile, or the volumetric flow rate through a little bit of area where the velocity doesn't change, that little bit of area, let me just kind of resketch this. Here's the picture again. So here's y, here's x. What I'm going to do is I'm going to look at cutting across this way and look at the volumetric flow rate through that little area, because the velocity doesn't vary much through that little area. This is my uy. That little area is going to be dx times the distance in and out of the page. I'll just call it w. Okay, so that's my little bit of area. So the volumetric flow rate through that little area will be uy times dA, which is just the dA is dx times w. And I'm going to integrate that as x goes from 0 to h, and that will give me my volumetric flow rate. Okay, so I can just substitute in rho g over 2 mu x squared minus rho g h over mu x plus capital U. That's going to be integrated times, that's going to be multiplied by dx times w. W is the distance in and out of the page, and then I have to do that integral. And if you do that and work it out, I won't go through the steps here, but it'll come out to be minus g h cubed. Oh, there's a rho there as well. Minus rho g h cubed, all divided by 3 mu plus UH. So that's what you'll get for the volumetric flow rate. Hopefully finding the volumetric flow rate using this approach seems very natural at this point. You've done enough problems where you have to integrate because you get a variable velocity profile, so you have to find the flow rate through a small area, like what I've shown here, which will just be uy times the little bit of area. Because over this small area, the velocity is well defined. It doesn't change much over that small area. And then we add it all up over the whole distance from 0 to h in the x direction. And then from here to here is just some calculus. All right, hopefully all that makes sense. We're going to go ahead and end the example there.